I am thrilled to announce Ari Gesher to this forum. And there are a few things that I'm going to talk about him. It's quite interesting. And you will see some of them during his talk. Some of them you're going to hear that now. He went to school with Max Levison at University of Illinois. And Max was the co-founder of PayPal. And he ran SourceForge.net as a senior admin and webmaster. And he spent 4 years doing improv comedy troupe. Are you going to have some joke here as well? Have some comedy here?
I don't know anything.
And as a bicycle messenger and a welder, hopefully this is prior to your last year, okay. And also he was brought in as an engineer number 2 to the current company that he's working on, Palantir, Gotham, who's building that new platform they have been building on. And the last one, this is I'm kind of puzzled. I'm going to listen what's going to be about. Listen to this. He is working on hacking Palantir's organization rather than the code. I have no idea what it is. I'm going to be listening to find out what it is. That kind of sounds fun, hacking the organization. With that, no further ado, please join me. Welcome, Ari.
Thank you, Sam, for the introduction. As he mentioned, I work at Palantir Technologies. I did a whole bunch of things beforehand. Used to work at SourceForge.net as the web developer and website maintainer, as well as running all the infrastructure there. Before joining Palantir about 7 years ago, was technically employee number 15, I think, but I was engineer number 2 on the back end of the Palantir Gotham platform, which I'm actually going to show you a little bit later. I worked for 4.5 years. As an engineer on our code base, building up the platforms, building up a lot of the underlying features that sort of drive a lot of what we do. But since that time, I've graduated to sort of move on to other things. As you can imagine, we're bursting at the seams from our perspective at about 700 people. And so today I sort of have enough context and understanding of what we've been through to sort of try to keep the organization together and understand how to keep all the moving parts of the people working together like it used to do when we were a lot smaller. But that's not what I'm really here to talk about tonight. What I'm here to talk about tonight starts, I want to set the scene in 1997, right? In May of 1997, Garry Kasparov loses a series of matches to Deep Blue, right? And it sort of looked at one of the pinnacles of human achievement that someone, IBM, was able to build a computer that could beat a human at chess, right? Some would call this a triumph of AI. But what failed to materialize after this sort of landmark match was the future that we saw in 2001, right? Where thinking machines would run large parts of what we're doing. In fact, we seem to be maybe even further from it than we were then. Things have come further, but we understand just how far we are. Because the state of the art today, as many of us have experienced, looks something like this. And for as cool as Siri can be sometimes, if you've ever tried to use Siri to get anything serious done, you know that maybe we still have a long way to go. So to figure out the roots of how this happened and where we are today, we got to look way back in history to the beginning of computing. So the beginning of digital computers was actually in military applications. And the first military computer, or the first digital computer, ENIAC, was used basically to calculate artillery tables, right? So the idea was you have some big guns, you want to put some rounds on target, you have to figure out if you have this much wind and this much weight, where do you put the settings to get it there? And they were monstrosities, right? They looked something like this, right? They were rooms full of wires and vacuum tubes. And in fact, at the time, the compilers were actually people. So the women actually that you see in that photograph was one of the compilers. Their job was to run around and plug in wires to like set up the program. And their job was actually called compilers. But around this time, right at the sort of very glimmer of the dawn of the computing age, there were a couple of thinkers who were very prescient around what we could do. So the two people up here on the screen, on the left is Vannevar Bush. And he was the founder of NACA, which later became NASA. He ran the precursor to the National Science Foundation, and he also oversaw the Manhattan Project during the war. And on the right is Jared Licklider. He was the early head of computing at ARPA, which later became DARPA, the organization that originally built the internet. He's sort of widely regarded as the Johnny Appleseed of computer science, just running around, planning ideas, starting things up. He came up with things like graphical computing. He was the first to imagine the internet. He ran the group at MIT that built Multics, which later became Unix, sort of very widely regarded for his ideas. So in this post-war period, they started writing down what they were thinking about where they thought computing was going to go. And so Vannevar Bush was sort of up next, and this is even before the war was over. In July 1945, in the Atlantic Monthly, he writes a piece called As We May Think, right? And in it, he imagines this thing called a Memex machine. And it's incredibly visionary. It imagines the world that we have today, but he had no sense of where the technology was going to go. So the way in which he described it was in the technology of the day. So it talks about electromechanical relays, thermionic tubes, photocells, keyboards, quote unquote, dry photography, and punch cards, right? And he talks about using microfilm to be able to shrink down the whole of the Encyclopedia Britannica, into something the size of a matchbox, right? So, but today we know that we could actually fit probably the whole of Wikipedia on a flash drive that's smaller than a matchbox, right? So very understood exactly what was possible even before it was possible, right? But in thinking about the relationship between people and computing systems, this is what he thought. And sort of there's some front matter there, but the most important part is that there's a separation of labor, this division of labor, right? So for mature thought, there is no mechanical substitute, right? You can't build a machine that thinks like a person. But creative thought and essentially repetitive thought are very different things. For the latter, there are and may be very powerful mechanical aids, right? So Licklider writes a paper in 1960 called Man-Computer Symbiosis, right? It was sort of before the politically correct time today, so I call the talk Human-Computer Symbiosis. And he found, in it, he sort of did some really deep introspection on the idea of research, right? His job is to run a research group, to be a researcher. And what he says is 85% of his time wasn't really spent thinking, even though that was his job. Quoting from him, hours went into the plotting of graphs and other hours into instructing an assistant how to plot. When the graphs were finished, the relations were obvious at once, but the plotting had to be done in order to make them so, right? Most time spent on matters that can be considered clerical or mechanical should be done by machine, right? So he just says, look, there's all these things that humans are good at, right? So humans are good at hypothesis formulation, advanced sort of fuzzy thinking, looking at new patterns that we haven't seen before, dealing with low probability situations like is the machine on fire, things that the programmer really didn't consider, and really being the visionary, dreaming about new and novel ways to do things. And machines are very good at other things, right? They're good at information retrieval, calculation, extrapolation, statistical analysis, brewing coffee to keep the humans awake, right? All the things that you can sort of do in this rote manner. And what he basically said in this paper was that the thing that you really need to do when building these systems, the right way to go, is something called intelligence augmentation, right? So the idea is figure out the division of labor. Anything you can automate, and then go back to the humans for the things that you can't automate. Figure out how to build a symbiosis between the human and the machine to build the most powerful systems that you can. Now, there's this thing that's happening in parallel. Somewhere along the lines said, wait a second, what if we could make machines that could actually think? Wouldn't that be awesome? We could do all kinds of stuff that we can't even imagine now. And so the idea of AI comes into existence. And the idea was born at something called the Dartmouth Conference in 1956. And what followed from this conference was what's known as the golden age of AI. This is from 1956 to 1974, and it's called the golden age of AI because basically what happened is if you said you were doing AI, someone would give you money, right? And you'll see there's this has actually happened a number of times where there's periods where people will give you money if you say you're doing AI, and then you don't produce AI and they take the money away, right? And this has happened enough times that the field of AI actually has a term for this. It's called AI winter, which is when they take the money away, right? So the first AI winter was in 1974, and it went to about 1980. From 1980 to 1987 was what's called the second AI boom, and that was where people were investing heavily in what are called expert systems and connectionism, which was trying to build sort of big models of the world, so you could encode everything that like a doctor or a judge or something knows, and ask them a question, and it would give you a diagnosis. Didn't really work that well. And then from 1987 on, there's sort of a second AI winter, because people are like, well, that didn't work. And there was sort of a shift into continuing the same kind of research, but calling it machine learning, right? They're like, well, we're not going to call it AI because people won't give us money then. And in New York Times in 2005 actually says, computer scientists and software engineers avoided the term artificial intelligence for fear of being viewed as wild-eyed dreamers, right? And in fact, a very famous AI researcher, Tesler's theorem, said that given everything that we know from the research that we've done and what we haven't produced, we'll just call AI whatever hasn't been done yet, right? And just to give you a sense of how wild-eyed this sort of dreaming was, here's a collection of quotes in chronological order from very famous AI researchers. In 1958, H.A. Simon and Alan Newell say, within 10 years, a digital computer will be the world's chess champion. So it was off by a few decades. Within 10 years, a digital computer will discover and prove an important new mathematical theorem. Hasn't really happened yet. In 1965, H.A. Simon says machines will be capable within 20 years of doing any work that a man can do. And for anyone who was around in 1985, we all know that wasn't true. In 1967, Marvin Minsky, who was sort of the grandfather of AI in a lot of ways, or sort of maybe the shaman is a better way to put it. Within a generation, the problem of creating artificial intelligence will be substantially solved. No matter how you measure generations, didn't happen. And in 1970, Minsky takes it one step further, and from 3 to 8 years, we will have a machine with the general intelligence of an average human being, right? So I happened to be around 1978. I wasn't actually yet paying attention to the field of computing, but I can tell you that didn't happen. So, and MIT News sort of summed this up in May of 2009. The field of artificial intelligence research, AI, founded more than 50 years ago, seems to many researchers to have spent much of that time wandering in the wilderness, swapping hugely ambitious goals for a relatively modest set of actual accomplishments. Now some of the pioneers of the field, joined by later generations of thinkers, are gearing up for a massive do-over of the whole idea. Evidently, they seem to think this is a new idea. They're like, we're going to reboot AI, forget about AI winter, right? So this keeps happening, right? And I don't mean this actually as an indictment of AI, because the pursuit of thinking machines has produced some amazing technology, right? And we use some of this every day. I mean, Siri, for all the problems with it, is fantastic. But the pathfinding that we use for navigation, everything from the personalized recommendations that you have from Pandora or Amazon, all these things come out of the field of AI, right? But we don't have thinking machines, right? And those are the real game changers. So the real question is, if you don't have thinking machines, what is the best way to build systems? And there's no question that these sort of statistical methods that we use in machine learning can solve certain problems. But there's got to be another way for different kinds of things. So you can think of AI as sort of happening in the software realm. In the hardware realm, something was happening in parallel. And this is a graph that should be fairly familiar to people. This is a slightly different telling of the same story. This is the calculations per second that you can buy for $1,000 on the open market, right? In 1960, which is about the middle of the graph, that number is 1, right? So for $1,000, you get about 1 calculation per second. This graph ends in 2000, but you can expect the trend to keep on going. So right now, we're at about 10 to the 9th or 10 to the 10th, right? About 10 billion calculations per second for $1,000. That's 9 orders of magnitude in 60 years. That has never, ever happened before in human history. This is like an amazing, amazing thing that I think we're still actually figuring out what the right way to use these machines is, right? Like the hardware has moved so fast, and Kevin Kelly actually did a little bit of research on this and has some great writing on it. Kevin Kelly's the original editor of the magazine Wired, and there's some work, if you go find his blog, kk.org. Moore's Law is actually all about research, applied research into miniaturization. And it gives you these kind of compounding gains that get you this kind of growth. But the fact of the matter is the hardware has grown faster than we figured out how to use it. And we'll go into that a little bit more. So, and this happened faster than anyone could really imagine. I go back to this is like incredible poetry in the words here of Vannevar Bush, right? A spider web of metal sealed in a thin glass container, a wire heated to brilliant glow. In short, the thermionic tube of radio sets is made by the 100 million, tossed about in packages, plugged into sockets, and it works. Its gossamer parts, the precise location and alignment involved in its construction, would have occupied a master craftsman of the guild for months. It is now built for 30 cents. The world has arrived at an age of cheap, complex devices of great reliability, and something is bound to come of it, right?